Good morning, everybody. My name is Lucian, and I will be your Yeba Physics tutor for today. Okay, this week is our final Yeba Physics sessions for this semester, and it will be dealing on temperature, the ideal gas law, and the first law of thermodynamics. Okay, now let me just go and check on my teams to make sure that we're all on the same page. Okay, seems to be the teams are logging in there. Okay, seems to be everything is streaming well. It's nice, and we're just waiting for 2 o'clock to hit. Just 2 more minutes, and we can start. Question number 1. So it hits 2 o'clock. Look at this. Good
Good
afternoon,
afternoon,
everyone.
everyone.
And let me just
Let me
switch
just
off
switch
here.
off here.
Okay, I've been sharing my screen with you guys. The screen. Okay, welcome to today's Yeba Physics. And my name is Lucian Pullen. And like I said earlier on when I was testing, uh, today or this week rather, we'll be focusing on temperature, the ideal gas law, and the first law of thermodynamics. That's what we'll be doing on this week, which is our last Yeba Physics sessions, 3 sessions for the semester. Then you're writing your tests, or you've already finished yesterday a test as well for PHYV. The AVV are writing on Saturday, and then you're all writing your exams after that. Now, they don't go much into the ideal gas law because you do some of that in chemistry, but I'm going to do some of it now, some of these problems. Okay, let's go immediately to question number 1, which states that you have 48 grams of oxygen, which is at room temperature. Okay, so you have oxygen at room temperature, and if, by the way, if you have questions, just ask me. So you have 48 grams of oxygen at room temperature. How many moles are in that 48 grams of oxygen? Okay, so 48 grams of oxygen at room temperature consists of how many moles? Okay, so moles, 1 mole of a substance contains Avogadro's number of constituent particles. Okay, that's what you were taught in high school physics. Okay, now how does one calculate the number of moles? The number of moles, N, denoted by N, let me try. So the number of moles denoted by N is equal to the mass of the substance that they give us over the molar mass of that substance. Okay, now N is the number of moles, M, small m, is the mass of the substance, and big M or capital M is the molar mass. Okay, now the molar mass is the mass that you get on the periodic table. Now the mass in this case is 48 grams. Okay, 48 grams. 48 grams. While the molar mass of oxygen, now oxygen is O2. Okay, one molecule of oxygen has a mass of 16 grams per mole. But oxygen is O2. Oxygen is O2, which means it has a molar mass of 32 grams per mole. We measure molar mass in grams per mole. Okay? So oxygen has a molar mass of 32 grams per mole. My apologies. I need to. Okay, there we go. 32 grams per mole. Molar mass is measured in grams per mole. Now, if you were to divide 48 by 32, let's do it quickly. 48 divided by 32 gives us 1.5. 1.5 mole. So the answer is 1.5 mole. Okay, so the number of moles in 48 grams of oxygen at room temperature consists of 1.5 mole. 1.5 mole. Let's check if 1.5 mole is indeed the correct answer. Okay, the options are 3, 1.5, 0.7, more than 3, less than 0.75. Let's check 1.5. And indeed, let's see. Did I go out now? 1.5, check. Yes, the answer is indeed 1.5. So we were correct in our calculation of the number of moles of oxygen in 48 grams of oxygen. The number of moles of oxygen in 48 grams of oxygen at room temperature. Okay. Question number 2. This is mainly going to be ideal gas laws, and then we're going over to temperature. So question number 2 asks, question 2, a bubble having a diameter of 1 centimeter. So we have a bubble, it has a diameter of 1 centimeter, meaning its radius, we can immediately say that the radius of this bubble is 0.5 centimeters. Okay, so we have a bubble having a diameter of 1 centimeter, and it's released from the bottom of a swimming pool where the depth is 5 meters. So the depth, or H, let's call it H, is 5 meters. Let's convert this to meters as well. 0.5 centimeters is just 5 times 10 to the negative 3 meters. It's 0.5 divided by 100. Now what will the diameter of the bubble be? Meaning this bubble's volume. What will its volume be when it reaches the surface? What will, note, the diameter of the bubble, if the diameter changes, the volume of the bubble changes. So if we can get the volume, we can get the diameter of the bubble. Now, what will the diameter of the bubble be when it reaches the surface? Remember, this bubble is at a depth of 5 meters in a swimming pool. It's released. Now, as you know,
Question.
Okay, speak.
Is the radius supposed to be 5 times 10 to the negative 2 meters?
It's half a centimeter, so it should be 5 times 10 to the negative 3, because it's just half a centimeter.
Okay.
You can check, if you divide that 5 by 1,000, you will get 0.5.
Okay, sir.
Well, you'll get 0.005 meters. If you were to multiply it by 100, you will get 0.5 centimeters. Okay.
Okay.
So we have this bubble. It has a radius 0.5 centimeters at a depth of 5 meters. Then we release it from the bottom of the swimming pool. We release it. It starts to float upwards. We want to know what's the volume of this bubble when it reaches the surface. They tell us additionally the temperature of the water at the surface is 20 degrees Celsius, while it is 15 degrees Celsius at the bottom. Okay, that makes sense. Pools are usually much colder at the bottom or than it is at the surface. Okay, and they also give us that the density of water is 1,000 kilogram per meter. Okay, first of all, we need to determine what's the pressure in this bubble at this depth in the pool. Okay, so what's the pressure of this bubble? Now, if you remember correctly, if you want pressure, okay, this was in fluid mechanics. If you want the pressure at a certain depth, you will take the atmospheric pressure and you will add the following: the density of the water multiplied by the gravitational constant multiplied by the depth at which this bubble or whatever it is, to get the pressure at that point in the water. Okay, now the atmospheric pressure is 101 times 10 to the 3. Okay, you can put there 101 0.01325. I'm just going to use this one. It's easier to me. That is the atmospheric pressure. Then you add to that the density, which is 1 times 10 to the 3. I'm not going to put the units in because I don't have space. That's 9,8. G is 9,8. And then the height is 5 meters. Okay, that will give you the pressure at that depth in this pool. Okay, now if you go to calculate all of that, you will find that the pressure at that depth is 15 times 10. Now note, this is in pascals. If everything is in SI units, your answer will be in pascals. Okay, named after Blaise Pascal. There it is, 15 times 10 to the 4 Pascal. So the pressure at the bottom of the pool is 15 times 10 to the 4 Pascal. Okay, now I'm going to erase this. So the pressure at the bottom of the pool, let's say pressure at the bottom is equal to 15 times 10 to the 4 Pascal. The temperature at the bottom of the pool is what? We were given that the temperature at the bottom of the pool is 15 degrees Celsius. 15 degrees Celsius. So in Kelvin, it would be 15 plus 273. Okay, so 15 plus 273. That would be your temperature in Kelvin, and that is 15. That is 8388. Okay, so it's 288 Kelvin. That's the temperature at the bottom of the pool. TB, temperature at the bottom. Okay. Now let's calculate at the surface. The volume at the bottom of the pool, we know we can calculate the volume of at the bottom of the pool. What is the volume at the bottom of the pool? Remember, this is a bubble, it is a sphere, so we can actually calculate the volume at the bottom of the pool. So VB is given, or we just take it as VB. Let's not calculate it. We can, but we don't need to. Okay, we don't need to for this problem, but let's just, rather than leave it out for now. Okay, now at the surface of the pool, the pressure at the surface. Okay, what's the pressure at the surface of the pool on this bubble? Okay, the pressure at the surface of this pool, it's going to be, we've already calculated it. Pressure at the surface is just the atmospheric pressure. The pressure at the surface of the pool is atmospheric pressure. The temperature at the surface of the pool is going to be 20 plus 273. Remember, we are converting all temperatures to Kelvin. So it's 20, that's 293 Kelvin. There's a 1.5 there also, but I don't use that. And then the volume at the surface of the pool. Now, from your ideal gas law, okay, we have the ideal gas equation. Okay, well, this is all the information. We have the pressure at the bottom, pressure at the surface, temperature at the bottom, temperature at the surface. Now let's see. We know from the ideal gas equation that the pressure at the bottom times the volume at the bottom over the temperature at the bottom should be equal to the pressure at the surface times the volume at the surface over the temperature at the surface. Okay. Let's plug in everything that we know so far. Let's plug in everything we know. The temperature at the surface, or at the bottom, temperature at the bottom is 288 Kelvin. The pressure at the bottom is 15 times 10 to the 4 pascals. And we have the volume at the bottom, VB. Then we have the pressure at the surface, which is just the normal atmospheric pressure, 10 to the 3. We have the volume at the surface, Vs, and the temperature at the surface, which in this case is 293. Okay. Now, if you were to work it out, you'll find out that VB, if you get VB alone, you'll have that the volume at the bottom is equal to 1.51 times the volume at the surface. Okay, the volume at the bottom is equal to 1.51 the volume of the surface. Okay? So the volume at the bottom is bigger than the volume at the surface. Okay, you can work that out, or you can actually work out here. you can actually work out VB because you are given the diameter. Okay? You can actually plug in the volume and then you get the volume at the surface and then work backwards to get the diameter again at the surface. Now, we have established now that the volume at the bottom is equal to 1.51 times the volume of the surface. Okay, so it is much bigger at the bottom of the pool than the surface of the pool. So the bubble has decreased in size. Oh, sorry, I switched this around. It should be the volume at the surface is equal to 1.51 volume at the bottom. Okay, I used V1 and V2. So when I just started denoting it VS and VB. Okay, so same thing. So it was wondering now why it should be expanding, not contracting. At the surface, it is much bigger. This bubble is much bigger because it's supposed to be expanding. Okay, because the temperature is increasing, which means the pressure inside is increasing, which means its volume, its pressure inside is decreasing, which means the volume should be increasing. That's why the volume of the surface is 1.5 times the volume at the bottom. Okay. Now we can work out. We didn't need to earlier on, but we can actually work it now out now. So the volume of the surface is equal to 1.5. Now we can calculate the volume at the bottom. Okay, you could have done this at the beginning, but we can do it now. The volume at the bottom is 4 over 3 pi times the radius, which is 1.5 cubed. And that all multiplied by 1.5 will give you the volume at the surface. Okay, 1.5 times all of that. And on this side, we don't actually need this. We can actually skip a step by just writing the volume of the surface is equal to 1.5. 1, the volume at the bottom. We can write the volume of the surface is 4 over 3 pi r cubed. That's the volume of the surface. And the volume at the bottom is just 4 over 3 pi r at the bottom cubed. 4 over 3 cancels, pi cancels, which leaves us with the following, that the radius at the surface cubed is equal to 1.5 times 1.51 times the radius at the surface cube. Now the radius at the surface is thus the cube root of 1.51 times the radius at the bottom. Sorry, that's the radius at the bottom. The radius at the bottom, which in this case is 0.5, and it's cubed. And that will give us an answer of the radius at the surface. Okay, now let's go check on the calculator. What is this answer? Okay, I did it it's the same way, but I just did it in symbol form. I actually added the numbers now. So the nth root, so the cube root of 1.51 multiplied, let's see if I did it correctly, multiplied by 0.5 cubed. That's 0.57. So the radius has increased to 0.57 meters. Okay, remember at the bottom the radius was 0.5 centimeters or 0.5 meters. 0.5 centimeters. Sorry, I just plugged in here. in centimeters. The volume is in centimeters, and this should be in centimeters. So the volume at the surface is now bigger. It's 0.5 centimeters at the surface, while at the bottom it was 0.57 centimeters at the surface, but at the bottom it was 0.5 centimeters. Okay. So let's see. What did the question ask again? What will the diameter of the bubble be? So the diameter, this is the radius. So we've calculated that the radius at the surface is now 0.57 centimeters. That's the radius. So the diameter at the surface will be double that. So it's going to be 1.14 centimeters. Let's see if there's an option for 1.14. The closest is 1.15 because I rounded. Let's see, am I correct? Go back. Yep, 1.15 centimeters. So yes, we are indeed correct when we were working out that particular problem. Okay, next one. Problem number 3 says a container with a 1 liter capacity at 27 degrees Celsius is filled with helium to a pressure of 2 atmospheres. Now 1 atmosphere is equal to 1 times 10 to the 5 newtons per meter squared. Now that is not exactly, it's actually 1,01325 times 10 to the 5 if you want to be more accurate. But they want to know how many moles of helium does it hold. Now you have all probably seen this formula before. Okay, PV is equal to nRT. It's the ideal gas equation. Okay, it's the ideal gas equation. Okay, where P is the pressure, V is the volume, N is the number of moles, R is the gas constant, and T is the temperature. Okay, now the gas constant can have various values, 3 main values, but we usually use it as 8,314. Okay, because we working in SI units. Now, they're telling us that a container with a 1 liter capacity, so 1 liter capacity, is filled with helium to a pressure of 2 atmospheres. So we have the pressure at 2 atmospheres. Okay, so the pressure, let's first, they want the number of moles, right? So let's make moles the subject of the formula. So it'll be N is equal to PV over RT. Okay. Now, what is the pressure? Let's convert the pressure. Okay, they are giving us the pressure in atmospheres. Okay, we want it in pascals. In pascals, the pressure is, it's 2 atmospheres, so the pressure will be 2 times 1 3. Okay, let me just use as they did, 1 times 10 to the 5. 1 times 10 to the 5. So there we have the pressure. It will be now in pascals because we are only using SI units. Okay, the volume is in liters. Okay, and 1 liter is 1 times 10 to the negative 3 cubic meters. Okay, this is in pascals. I converted from atmospheres to pascals. Okay, if you did the whole conversion that we did in first semester, which you should be so good at right now because you're going to write an exam on it, R is equal to 8,314, and it has units. Okay, but I'm not going to include them there now. And then, of course, temperature in kelvins, it's 27 degrees. So, okay,
Can I ask?
you can ask.
There you wrote 2 multiplied by 1.0 times 10
To the 5.
exponent 5.
Yes.
Oh, okay. Okay, thank you.
Okay. Then we have the gas constant here as R, and then T is 27 degrees Celsius, which we should convert to kelvins. Now if we convert to Kelvin, we just add 273.27 plus 273. Usually I add 0.1.5 as well. Okay, this is the full conversions, 0.15, okay, to get Kelvin. Now if you were to work this out, I'm not going to test your calculator skills. You can go and work this out for yourself, but you will get this number of moles, 0.081 mole. This is the answer, 0.081 mole, if you were to plug this in on your calculator. Okay, I'm not interested to know how well you can plug stuff in. I want you to understand what is happening. So we have to use an ideal gas equation. Now normally if they don't tell you it's an ideal gas, then you just assume it's an ideal gas. Okay, because if you're not assuming, then you have to use van der Waals equations and all of that, and that just becomes very complicated. Okay, then you delve into the realm of physical chemistry. So we picked 0.08 as the answer. Let's check. And yes, we are correct. It is indeed 0.081 mole. Okay, question number 4. Let's look at what question number 4. It's another ideal gas problem. It says an auditorium has dimensions 10 by 10 by 60. Okay, 10 by 10 by 60. So volume is equal to 10 by 10 by 60, all in meters. So the volume will be in cubic meters. So it's 10 times 10 is 100 times 60 is 6,000 cubic meters. So 6,000 cubic meters is the volume. That's in an auditorium. They asking us how many moles of air fills this volume at 1 atmosphere at 0 degrees Celsius. So the temperature is at 273.15 Kelvin. That's the temperature at 0 degrees Celsius. 1 atmosphere is a pressure of 1,0 times 10 to the negative 5 pascals. Okay, that's the pressure. And they want to know how many moles. And we established earlier on that N is equal to PV over RT. Now we have all of these values, all of them. P, the pressure is 1 times 10 to the 5. The volume is 6,000. R is 8,314. And the temperature is 273.15. Now if you were to work that out, just plug it in on your calculator, you should get an answer of 2.68 times 10 to the 5 mole. So this is how many moles there will be. 2.68 times 10 to the 5 mole. Okay, it's basically the same question as the one before. 2.68 is 2.7 times 10 to the 5. So this is the only one that has 10 to the 5 in it. They rounded. I did not round. So 2.7 times 10 to the 5. We can check. It is correct, 2.7 times 10 to the 5. Okay, now if at any point you don't understand one of the problems, I'm trying to, they are all reasonably easy problems, so I want to see how far I can go. Okay, now this one here is, I'm going to try and do it this way first. Then I'm going to do, I wonder, this is the easiest way to do it. This is the pressure. Let me just write it. This is number 5. So we have that Charles's law. Is it Charles's law? Pressure over T1 is equal to pressure 2 over T2. Okay. This is variations of the gas laws. This is a constant volume. It's a constant volume gas thermometer. So we can write in V1 here and V2 there. Okay. But it's constant volume, so they will just cancel, leaving us with P1 over P2. P1 over T1. Oh, okay. Since it's constant volume, they will cancel each other. Now, they telling us that a pressure of 10 millimeters mercury, so 10 millimeters mercury, Hg is mercury if you don't know by now, and a temperature of 3, they say at 50 degrees Celsius, that we measure a pressure of 10 millimeters mercury. Okay, so 50 degrees Celsius is 3.15 Kelvin. Okay, just convert the temperatures to Kelvin. I worked the pressures, I left the pressures. We want pressure number 2, the pressure at the 0 point, meaning at 0 degrees Celsius. In other words, at 273.15 Kelvin. Okay, that is what we want the pressure at. Okay, so let's see what this gives us. Okay, let's see if we're right. So it will be 10 divided by 323.15, and then we multiply that whole thing by 273.15, and the answer is that the pressure at 0 degrees Celsius, or at the 0 point, is equal to 8.45 millimeters mercury. That is the pressure at the 0 point. Okay, so that would be the pressure at the 0 point. Let's check if and see if there's an option for 8.45 millimeters mercury. So we have 31.8, 11.8, 8.45. That's the one we want. Let's check it. I must say this is on question number 5. 8.45. In order to answer this problem, 8.45 is correct. In order to answer this problem, you need to know that the triple point of water is 273.14. Or just the triple point, that is just 0 degrees Celsius basically. Okay, it's just a fancy way of saying 0 degrees Celsius. Okay. Let's look at question number 6. The rest should be fairly easy by now. We are just going to run through them. Question 6, I'm not going to keep you more than an hour. Question 6, they ask, at which of the following temperatures would 1 liter of water weigh the most? Okay, now at which of the following temperature would 1 liter of water weigh the most? Now let's see. Okay, mass, mass is what determines the weight. Okay, the mass is what determines the weight. Now mass we know is equal to the density multiplied by the volume, that is mass. Okay, now the volume is the same for all of them. The volume would be the same, 1 liter would be for all of them. Okay, so what is going to affect the mass in this case is the density at all of those temperatures. Okay, so the density at all of those temperatures. Okay, now I want to teach you something that or maybe you've known this from high school, that at 4 degrees Celsius, water is at its most dense. So at 4 degrees Celsius, water is at its densest, okay? Meaning at 4 degrees Celsius, it will have the highest mass. So at 4 degrees Celsius, water would be at its densest, meaning its mass would be higher. So the water would weigh the most at 4 degrees Celsius, because at 4 degrees Celsius, it is at its densest. And right after 4 degrees Celsius, it begins to get less dense, okay? Let's say this is a density curve, okay? This is 4 degrees Celsius, this is 0 degrees Celsius, and this is continuing, this is degrees Celsius, and here we have density. Okay, on this axis we have density, and on this axis we have volume. Now at 4 degrees Celsius, the density would be at its highest. Okay, the density would be at its highest. It would begin to decrease because ice floats on water. Okay, but there the water would then be, the density would be going down or fluctuating, whatever. But at 4 degrees Celsius, its density would be at its highest. Now when its density is at its highest, its weight will be at its highest. So we'll check 4 degrees Celsius, and that is indeed correct. So now you know that water will weigh the most at 4 degrees Celsius. Okay, so if you want to carry, say, a 20 liter of water, okay, try not to carry it at 4 degrees Celsius, because it will be at its heaviest at that point. Question 7. In order for two objects to have the same temperature, okay, I'm going to leave this one up to you guys. Okay, I want to know, those of you that are tuned in, let me just check, where are you? Okay, those of you that are currently tuned in, okay, Olarato, Amashe, Tabiso, Lungani, Vusani, Tashinga, I want you guys to answer the following question. This one, question 7. In order for two objects to have the same temperature, they must have what? Be in thermal equilibrium, be in thermal contact, have the same relative hotness or coldness when touched, have all the properties listed above, or have only the properties of B and C above. What must be the condition so that they must have the same temperature? Okay. If you have done the 0th law of thermodynamics, if you're an FEV student, you'll be doing it tomorrow. If you are PHYV student, I don't know if Dr. David has done it with you again yet, but the 0th law of thermodynamics say that two objects that are in thermal equilibrium have the same temperature. Okay, so that is me basically giving you the answer. They must be in thermal equilibrium to have the same temperature, and we can check if they are in thermal equilibrium, they have the same temperature. Okay, if they are in thermal equilibrium, they have the same temperature. The answer is A. When they are in thermal equilibrium, they have the same temperature. That is straight derived from the law of the 0th law of thermodynamics. Okay, and why it's called the 0th law is because they first got the first 3 laws, and then they realized, oh, we didn't actually define temperature, let's go back and define it. But they've already have law 1, law 2, and law 3, so they defined the law as the 0th law, meaning the 0 law should start before 1. Now the 3 laws of thermodynamics, the first one, the 0th law, is actually defines temperature for us, gives us a method of defining temperature, while the first one is the law of conservation of energy. Basically, it's a special case of the law of conservation of energy. The second one states that the entropy of the universe will always increase, and the third one, can't remember exactly what the third one states. I've forgotten what the third law of thermodynamics is, but it'll get back to me. Okay, question number 8. Let's erase this. Let me just check something. Third law of thermodynamics. The third law of thermodynamics. Oh yeah, this is the second law. The third law just states that the entropy of a perfect crystal at 0 Kelvin is 0. The entropy is 0. Basically saying nothing is moving, happening at 0 Kelvin. So question 8, but that is beyond the scope of the first year. That's what you do in second and your honors year in physics. Question 8, 1 mole of an ideal gas. So we have an ideal gas, okay, and we have 1 mole of it. Has a temperature of 25 degrees Celsius, okay, so if the volume is held constant and the pressure is doubled, the final temperature will be, okay, so we have that the volume is held constant, so we have P1 over T1 is equal to P2 over T2. Because the volume is constant, we can use this formula. Now they're telling us that what is the final temperature in degrees Celsius, okay? I did it in Kelvin, but let's see if I work it out in degrees Celsius. Or anyway, 25 degrees. The pressure is 25 degrees. At a temperature 25 degrees Celsius, the temperature is P1. But at a temperature, at some temperature T2, the pressure is doubled, so it's twice P1. Twice P1. Now you can actually work out what T2 is. That is what we want, the temperature. At what temperature will it be? Will the pressure double? Okay, so if you solve for T2, if we were to solve for T2, we would get that T2 is equal to 2P1 over P1, which is this one, multiplied by 25 degrees Celsius. P1's cancel, so it's 2 times 25. It's 50 degrees Celsius. But these temperatures are all in. They're all in degrees Celsius. So if they're in Kelvins, it's 323. So these temperatures are all in Kelvins. Okay, that's what I was afraid of. So the final temperature in degrees Celsius will be 50 degrees Celsius at 2 times the pressure. That means the final temperature will be, let me just get it. So it will be 50 degrees Celsius plus 273. That will give us 323.15 Kelvin. 323, and that is what is there. Okay, I've had a problem with this answer because they're asking us if the pressure is doubled, the final temperature in degrees Celsius. They want it in degrees Celsius, which means it will be 50 degrees Celsius, the pressure. But if it's in Kelvins, it will be 323 Kelvin, which is not in let me do the whole thing in, I'm going to do the problem again, but I'm going to do it in Kelvin like I originally did. Okay, it's P1 over P over T1 P2 over T2. Just note now, when it's in Kelvin, it's 298. Is this question 8? 298. It's 25. 298.15 Kelvin. And T2 is what we want. That'll be 2P1 and that'll still be P1. The same thing, but I just converted the temperatures to Kelvin. Okay. Now if you were to work it out, same way, you will get that the temperature now is equal to, pressures will cancel, it'll be 2 times 298.15 Kelvin. That'll be your pressure in kelvins. Okay, now 298 times 10 to the, that is 4, that's 5 something. Let me just do it quickly before I mess up again. I already did it in Kelvin, so it is 2 times, but the answer is correct still, 98.15. that gives me 596. So T2 is 596.3 Kelvin, but we don't want the temperature in Kelvin, we want it in degrees Celsius. So in degrees Celsius you should subtract 273.15, and that gives you 323. So that's 323.15 degrees Celsius, which is what we should get here, and we just did 323 degrees Celsius. So it is indeed Celsius. There, 9, question 9. 1 mole of an ideal gas. If you just see the word ideal gas, it's PV-nRT, it's the ideal gas law. Okay, so we have 1 mole of an ideal gas at constant volume of 1 liter. So we have a volume. Find a change in pressure if the temperature increases by 50 degrees Celsius. Okay, so first of all, let's work out the original pressure. P1 is equal to nRT over volume. Okay, now N is 1, R is 8,314, the gas constant. The temperature is 50 degrees Celsius, or we can just choose it to be 0 degrees, 273, because there's a change by 50 degrees Celsius. So it's 273.15. Let's say it's at 1 degree Celsius, it has this pressure, and it is a volume of 1 liter, which is 1 times 10 to the 3 cubic meter. This gives us a pressure, original pressure of 2,27 times 10 to the 6 Pascal. So this is the original pressure, 2,27 times 10 to the 6 Pascal. That's pressure 1. But then we increase the temperature by 50 degrees Celsius, okay? So the original pressure, pre-1, is equal to 2,27 times 10 to the 6 Pascals. So what is pressure 2 then? The second pressure, if it's increased. Now, what do we expect to happen when we increase the pressure, the temperature? Okay, when temperature increases, the volume increases, which means the pressure decreases. Okay, pressure decreases. But if the volume is held constant, okay, the pressure will increase, because pressure is directly proportional to temperature. That is Charles's law. Okay, from high school physics, that's Charles's law. So in this case, pressure 2 will be higher because of a higher pressure, a higher temperature. Now same way we work out pressure number 2. Still 1 mole, that hasn't changed. The gas constant is still 8,314. The new temperature is 323.15 because it has increased by 50 degrees Celsius, okay? And the volume is still the same, 1 times 10 to the negative 3 cubic meters. And this gives us a pressure of 2,6. So P2 is 2,69. And like we just said, the pressure will be higher. Okay, so this is the new pressure, P2. Now to find the change, they want the change in pressure. So P2 minus P1 is equal to 2,69 minus 2,27 times 10 to the 6. That gives us an answer of 4.2 times 10 to the 5. 4.2 times 10 to the 5 pascals. This is in pascals. 4.2 times 10 to the 5. Now if you were to convert 4.2 times 10 to the 5 pascals, okay, if you convert from pascals to atmospheres, you just divide by 1. If you divide this by 1 times 10 to the 5, you will get approximately that it is going to be 4.1 times 10, 4.1 atmospheres if you were to convert it to atmospheres. No, not 41, 4.1. Okay, so or 4. In this case, it's 4.2 times 10 to the 5. You are actually dividing not by 1 times 10 to the 5, that is just me. You are dividing by 1,01, which will give you approximately 4 atmospheres.
So can I see your workings for P1 before you proceed?
Okay, the workings for P1. I just erased it. It's exactly the same as this one. Sorry. This is P2. Now the workings for P1 is exactly the same as this one. Okay, it's N R T over volume V. Does that okay? So it's just P is equal to nRT over V, the pressure. So first I calculated P1 using the temperature of 0 Kelvin, or not 0 Kelvin, 273 or 0 degrees Celsius. But then they say it increases by 50. So you could have chosen any arbitrary temperatures, but the difference between the temperatures must be 50 degrees Celsius.
Okay, sir.
Okay. So this is just for atmospheres. If you convert it to atmospheres, I'm not going to go into the whole how you convert from atmospheres to from pascals to that. You already know how to convert. Okay. The rest of them are easy. There are no real calculations from this point on. Okay. That was question 9, was it? Yes. So let me just check question 10. These are just knowledge based. Okay, so 1 mole of an ideal gas is held at constant. Okay, that I already did that one. Question 10. Two bodies can be in thermal equilibrium with one another when they are at the same temperature, even if they. So two bodies can be in thermal equilibrium, meaning there is no net flux of temperature from one another when they are at the same temperature, even if they absorb different quantities of thermal energy from their surroundings in equal intervals. They have different masses, they have different volumes, they have any of the properties listed above. That. Okay, so they can be at this in thermal equilibrium if they absorb different quantities of thermal energy from their surroundings. They can be in thermal equilibrium if they have different masses. Yes, they can be in thermal equilibrium if they have different volumes as well. Okay, so if they have any of these 3 properties listed above, they can be in thermal equilibrium, and we can check this question. Okay, so question 11. 2 moles of an ideal gas. So 10 is number D. 11. Question 11 is 2 moles of an ideal gas are placed in a container of adjustable volume. When measurements are made, the pressure is inversely proportional to the volume at constant temperature. Pressure at constant at constant temperature, pressure is inversely proportional to volume at constant temperature if temperature is constant. That is correct. That is called Boyle's law. Now, the temperature is directly proportional to the volume or constant pressure. Now, so temperature is directly proportional to the volume. This is called Gay-Lussac's law. Okay, this is Gay-Lussac's law if the pressure is constant. The temperature is directly proportional to the pressure, so P is directly proportional to the temperature. This is Charles's law if the volume is constant. These three laws are what govern our study of gases in the ideal condition. So all three of these are correct. Okay? All the statements above are found to be correct. All of those statements are indeed correct. Now, 100-gram cube of ice is heated from negative 120 degrees Celsius to positive 120 degrees Celsius. In which of the following processes is the greatest amount of energy absorbed by this material? Now, the greatest amount of energy absorbed by heating ice to 120 degrees Celsius is when we are turning the water to steam. Okay, so when we are melting the ice, not we are vaporizing the water to become steam at that point, because the heat of vaporization, the latent heat of vaporization is higher at that point. It's the highest, it's higher than the latent heat of fusion, and the specific heat does not compare even at those big temperature ranges. Okay, if you have not done the first law of thermodynamics, later on when you watch this again or something, you will see what I was talking about. Now, number 13. Okay, 100-kilogram student eats a 200-calorie donut. Okay, to burn it off, he decides to climb the steps of a tall building. How high in meters would he have to climb to expend an equivalent amount of work? Okay, so first we need to work out how many calories he needs to burn. Okay, so we need to work out how high he has to climb. Oh wait, is this part of my question set? I'm not sure now. Is 13 part of my question set? Okay, let's work this out. Okay, so how high in meters would he have to climb to expend an equivalent amount of work? Okay, so to expend the equivalent amount of work, how high would he have to climb? Let's see. So we have a 100-kilogram student, right? Let's first work out how much energy is in that 200 calorie. Note that that calorie is big, is a big capital C. Okay, so 200 calorie multiplied by, there is 1000 calories, small calories, in 1 calorie. This is 200 calories. So we are converting from calories to small k calories. Okay, but we don't actually want calories, we want joules, and there is 4,186 joules in 1 calorie. This is just a kilocalorie, which means in that 200 calorie donut there is approximately 837,200 joules of energy. So he needs to climb a height that uses this exact amount of energy in order to burn off that donut as he so wants to. Okay, now we check something here. I want to check if I have the correct formula. There are two ways of going about this, but if you thought you would escape your mechanics, you were wrong. Now work, we know, he's climbing the steps of a tall building. Now work is equal to F dot D. Okay, now this is where I have a problem with this particular problem. Okay, because he climbs the steps of this tall building, and we can work it out this way, but that is incredibly difficult. Okay, that is incredibly difficult. Well, not incredibly difficult, it just takes too much time. Okay, so we will work on this one. The work he does should be equal to mgh. Okay, he'll be working against gravity, he'll be climbing up. Okay, so the work he does should be mgh. Okay, his mass is 100. Now the work, how high should he climb? We want to know how high should he climb. Okay, now let's first solve for h. H is the height he should climb. The work is equal to the amount of work or the energy that's in the donut. Okay, this is then divided by mg. The energy we calculated in the donut is 837,200 divided by 9,81 multiplied by the mass of the student, okay, which is 100 kilograms. And that will give us a height. So how high he has to climb. This does not take, this is only the potential energy. Okay, this is, well, this is energy, but it's potentially how high he has to climb. He will not be able to just climb straight up. He's climbing in a circle, which means a lot of factors are into play, but let's just do it as they want. Okay, this is how I would do it. The person whose mic is on, can you just switch on off your mic, please? Let me just check whose mic that is. Okay. Seems they have switched it off. Clear. This is my last question, by the way, for today. It shouldn't be 9,81. Sorry, that should be 9,81 multiplied by 100 is 981. So it's 837,200 divided by 981. So 853,4 meters is what I would say is the distance that the student must climb to burn off that 200 calorie donut. So 854 meters, okay? And there you have it. Okay, that's the distance that the student must climb to burn off those calories. Okay, and that is all that we have time for today, ladies and gentlemen. Hope to see you next, or join James Arnold tomorrow, and then James the day after that. Okay, all the best and good luck with all your assessments. If you have any questions, you can ask.